Let's look at thermochemistry. And as the word states, thermochemistry, it's about thermo meaning something to do with heat, okay, and energy. So we're looking at the energy concepts in chemistry or in chemical reactions. So first of all, let me introduce you to the concept of thermodynamics, because thermochemistry is a portion of thermodynamics, which is a huge part of learning about chemical reactions. So first of all, thermodynamics is the relationship between the heat and other forms of energy. And then thermochemistry is going to be just a little bit portion of the thermodynamics. And in this one, we'll study only about the heat absorbed or evolved by chemical reactions. Now, it's not just absorbed and evolved, it's also about the quantity, okay, of it. So it's not just qualitative, but quantitative as well that we're going to talk about. So then we need to talk a little bit about energy also. Energy is defined as the capacity to do work. One of the things that you might remember from your Gen Chem 1 is we talked about conservation of matter, and that was Dalton's atomic theory. So in conservation of matter, we said that matter cannot be created nor destroyed, and the same thing goes for energy also. Okay, so that energy cannot be created or destroyed. It can only be converted from one form to another. So these are the forms of energy. For example, electrochemical, mechanical, chemical, nuclear. That's a form of energy. And then there's another thing called the source of energy. And the source of energy can be, for example, for solar energy, it would be the sun. For nuclear energy, it would be nuclear reactions and so on. Okay, so these three are important things. Now, we're going to talk about thermodynamics a little bit in this chapter, and then we'll pick it up later on also. All right, so in this one, we'll focus more on just the study of heat, okay, in chemical reactions. So a little bit about then energy and its units. Okay, so because we are talking about energy in this chapter. So first of all, the most common unit of energy is calories. Okay, but calories are also the non-SI units, although it's a very common unit, but this is considered to be the non-SI unit. 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So that is how we make the calorie a uniform unit, and we know how much it is. Okay, so that's how calorie is defined. However, the SI units of energy are actually joules, okay, which is represented by capital J. And the conversion factor for 1 calorie is to joules is 1 calorie to 4.184 joules. Now, one other thing you might want to remember, and this is kind of an important thing, but not so important, but kind of important. All right. So here, 1,000 calories is equal to 1 calorie. Now, there is a difference between this cal and this cal looking at this C. Okay, so this is a small case C and this is a capital C. And the capital C actually indicates 1,000. Now, generally, you could also call it kilocal, which in this case, it would be the small c, all right? So, but anyhow, 1,000 calories is represented as 1 capital C cal, all right? And this is the unit that we use a lot more in food calories. Usually in chemistry, when we're talking, we'll probably use kilo or we'll use joules. But in food calories, for example, one's capital C calorie means 1,000 calories. Okay, so the two most common forms of energy that you will encounter is kinetic energy and potential energy. And the strange thing is that you don't really encounter those. They're always there. You just don't think about it. Okay, so kinetic energy, for example, is the energy of motion, which is given by this formula. And potential energy is energy of a stationary object. Now remember we said in the previous slide that energy cannot be created nor it can be destroyed. So which means that everything has energy, okay, because all you're doing is converting one form of energy to another form of energy. So everything has energy. So if everything has energy, then you have to be able to define that energy. So if anything is in motion, it's called kinetic energy. If anything is stationary, then it would have potential energy because it has the potential of energy. All right, so for example, a table that is just stationary, that's just sitting, has potential energy. The moment you take the table and throw it somewhere, that will turn into kinetic energy then. Okay, so those are the two most common forms of energies that you will encounter. Now for something what is called the internal energy. And the internal energy of any system is a sum of kinetic and potential energy of all particles. So for example, the energy total of any system is given by the sum of kinetic, potential, and internal energy. So internal energy actually comes from the particles, okay, that are in there, whereas the kinetic and potential may come from other things also. All right, so the total energy, okay, would be the sum of all of these things. And so remember that this is what drives the conservation of energy, all right, which is that energy cannot be created nor destroyed, because energy is the total sum of all of this. Now, what we generally study is not really the exact internal energy that anything has, because that is sometimes a little bit hard to measure. So what we generally study is the change in the internal energy. So what was the initial energy and what was the final energy? So that's what we generally study. And so delta here, the little triangle, that means change. So the change in the internal energy is the final energy of the system minus the initial energy of the system. So this gives us an idea of how much energy changes have been occurring. The internal energy in general is an extensive property and a state function. First of all, an extensive property depends on the quantity of the substance, and a state function, okay, which is the first time you're hearing this. So the state function is a property that depends only on the present state, okay, which is then determined by variables such as temperature and pressure. So for example, if you have a present state of gas or solid, that is what a state function is, okay, and what happens with the state function, okay, is that it depends only on the present state, okay? So whatever you start with and whatever you finish, how you get there, it's not so important as to what it was to begin with and how it was as the final, okay? So initial and final is most important. How you got there is not so important, okay? So for example, this is shown by this little diagram here or picture here of a campsite. So these are the state functions, the fact that you have a campsite over here and there is a campsite on the top there, okay, A to B. How you get from A to B is not so important as to the fact that A and B are at that particular stage. You can go like this or you can go in a very zigzag manner, okay? But that is really what the state functions mean, is that there is a particular location of these things, but not how you get there, okay? So that is what a state function means. And then when we study chemical reaction, we actually study them in a system, which is actually called a thermodynamic system. And it could be a reaction vessel like an Erlenmeyer flask or a big setup. It could be a big, chemical reactor that we have, but that would be a thermodynamic system, okay? And so in the system, we have the actual place where you have the reaction going on, and then you have all the surroundings, okay, of the system. So what we study then when we talk about the changes in the system that are going on is between the system and the surroundings, okay? And so the energy changes that we study are between these two things here, the system and the surroundings. And generally what we end up studying then is the heat, okay? And heat is a very abstract concept because heat is very hard to explain to somebody. However, the only way you can measure heat is by the change in temperature, okay? But heat is some sort of a sensation that you can feel. And so it's a little bit of an abstract thing, okay? But heat is the energy that we talk about here, and that is what we measure in terms of flowing in and out of a system, okay? And the way we do it is, of course, by measuring the temperature of the system. So when the heat is absorbed, Q, which is the heat representation, the Q is positive, okay, and which means that the heat is added to the system, so which means that heat is absorbed, and that's called an endothermic process. The reaction vessel is going to feel cooler because now the heat has been removed from the vessel and it's in the system. When heat is evolved, then Q is going to be negative. And that means that the heat has been removed from the system, which means now the vessel is going to feel warmer because now heat is coming out of the system, and this is called an exothermic process. Okay, and so the reaction feels warmer because the heat is coming out of it. All right, and then there is something called the heat of reaction, and the heat of reaction is the value of the heat, or the Q, that is required to return a system to the given temperature at the end of the reaction. Okay, so that's called the heat of the heat of reaction. So here again is a little bit of summary for you for exothermic and endothermic, because these are some things that we will talk about a lot. So again, in an endothermic reaction, the vessel is cooler, the heat is absorbed, energy is added to the system, and then Q is positive. And for or exothermic reaction, everything is opposite. Okay, so reaction vessels is warmer, heat is evolved, energy is subtracted from the system, not added, because it is now given off, and then Q is going to be negative, and Q is the value. A little bit about enthalpy and internal energy. Okay, now enthalpy is H, and this is again the first time you're hearing something which is called enthalpy. Enthalpy H is what we call internal energy plus the pressure and volume. Okay, now remember we talked about state functions just a little while ago, and state functions we said that are at a particular pressure and volume. So H here is equal to U plus PV. Okay, so H is equal to internal energy plus pressure and volume. Most of the reactions will take place at a constant pressure, which means either at at atmospheric pressure or at some sort of a constant pressure. So which means that now we can change the other conditions. So which means that delta H is equal to delta and delta internal energy plus pressure, which is constant, and the change in volume then. Okay, so this is how it can be represented, or we can rearrange the equation and put the internal energy on the left hand side and show the change of enthalpy over here. Enthalpy has to do with the heat, okay, of a reaction. So really we're trying to quantify this a little bit different than Q would be, because Q is also a measure of heat, okay, and so we're trying to quantify it in a little bit different way. So the negative P delta V is the energy needed to change the volume against the atmospheric pressure. Okay, and so that is what we mean by this equation. We couldn't have seen it from here, but we see it over here because this is now represented by delta U, okay, on the left hand side of the equation. So for example, if you have a simple equation like sodium reacting with water to give sodium hydroxide and hydrogen gas, the hydrogen gas over here will have to do some work to raise the piston over here because it's releasing the gas, so which means that the reaction is actually doing some work and releasing the piston, and so the piston is raised now. At the same time, energy is involved, so 368.6 kilojoules of energy are evolved, okay, at this process. So heat is being evolved, work is being done, and there is a change of volume. All right, and the change of volume occurs because pressure is constant. This is also something to do with gas laws, if you can remember. So then coming back to the enthalpy of reactions again, enthalpy is again measured as a change, okay, not really as enthalpy by itself. So enthalpy, the change of enthalpy is studied then at a given temperature and pressure, all right? And so delta H is going to be then H of products minus the enthalpy of reaction of the reactants, products minus reactants. If you think back to a few slides, you will remember we said the same thing about internal energy also, final minus initial. That was the internal energy, and now we're saying the same thing about enthalpy also. So all of these things are kind of related. So products minus reactants, that's what delta H would be. So for example, when we have this kind of an equation yet again, the sodium equation, this is how it can be written down. Okay, so if you start with this equation here, 2 moles of sodium, this is going to be at a higher energy, and by the time you do the reaction, this much amount of energy has been released. Okay, so the enthalpy of the reaction is given by 368.6 kilojoules, okay, of energy that has been released. So then we come to what is called thermochemical equations. In thermochemical equations, we try to represent the equation and the energy, the changes in energy involved in this. So now we're going to stick a lot with the delta H. We will not talk about internal energy until later on. So we'll stick with delta H, okay, which is again, remember the changes of heat going on from reactants to products. All right, that is what delta H is. So for example, when you write this reaction out, this is how you would write it. We just talked about it in the previous slide where you have sodium reacting with water to give sodium hydroxide and hydrogen gas. So once you have this, delta H is equal to minus 368.6 kilojoules. Now this minus here indicates that this is an exothermic reaction. This is the delta H, of course, which means that products minus reactants is minus 368. That's the amount of energy that is given off, okay, at this point. Now, this equation over here, if you look at it, it is a balanced equation. All right, so it's really important that you balance your equations when you do thermochemical equations. So let's look at an example. Okay, write a thermochemical equation for the combustion of sulfur 8, which produces 9.31 kilojoules per gram of sulfur at constant pressure. All of the reactions we're going to do are going to be at constant pressure. So even if I don't mention the pressure, it's still constant pressure. So the first thing we have to do is write the equation. So it says combustion of sulfur 8, combustion meaning burning something in oxygen. So the first thing we have to do is write the equation. The product that is produced is sulfur dioxide. So this is the balanced equation that we get. Okay, and then what we do is we convert the heat per gram to heat per mole. All right, because this over here, kilojoules, is going to be per mole, not per gram, because this is equations are written in moles and not in grams. So then we convert the delta H, okay, that we are given over here to moles. So how do we do that? So we have delta H, which is 9.31 kilojoules per gram. Okay, that is what is given to us. It's per gram of sulfur 8. And then we convert the gram of sulfur 8 to moles. Okay, so it's kilojoules per mole. And so then delta H comes out to be negative 2.39 times 10 to the negative, 10 to the power of 3 kilojoules, right? So then we can go ahead and write the entire equation. And this is then the final equation where you have the balanced equation and then the delta H, which is going to be negative because it says it produces 9.31 kilojoules, which means that the heat is released. If it is released, then the sign has to be negative over here. So the 2 or 3 things that we did over here is first write an equation, then we balanced it out, then we converted grams to moles, okay, when we write this equation, and then finally when we wrote this equation. And then finally when you write the equation out, then you make sure that you have the right sign for delta H. One of the most interesting things about thermochemical equations is that you can actually manipulate them. And the manipulation can occur only because the delta H, which is the enthalpy, is a state function. State function meaning that it is at a particular location. Remember the graph that we saw, point A to point B. So you have to go from point A to point B. How you get there is your choice. Okay, and so you can manipulate thermochemical equations only because of that reason. All right, so for example, if you multiply an equation by 2, then you can multiply delta H by 2 also, okay, because again it's a state function. So if everything is doubled, then delta H must also be doubled. And then if an equation is reversed, then the sign of the delta H is also reversed, okay, which means that if your forward reaction is exothermic, then the reverse reaction must be endothermic of the same value. Okay, why? Because again delta H is a state function. It's at a particular location. All right, so that's why you can actually manipulate thermochemical equations, and I actually find this quite fun, okay, to do. So let's take an example, okay, where we have methane, which is reacting with water to give carbon monoxide and hydrogen gas, and the delta H here is 206 kilojoules. The sign here is not there, which means it's positive. So usually you will see positive written over there, but anyhow, in case it's not written, just assume that it is positive, which means that it's an endothermic reaction. All right, so then the question is, which of the following is the most exothermic reaction? Now remember, the initial reaction given to us is endothermic. So then out of these four equations, which is the most exothermic reaction? So here are the equations. Okay, now let's look at the first one. The first one is the same as what we had before. All right, so which means the delta H must be the same. Okay, it can't be any different. The second reaction is still the CH4, which means methane is still on the left hand side. However, now we have 2 moles of methane. Okay, 2 moles of water. Everything has been doubled. Okay, the 3 moles of hydrogen that were coming out now are 6 moles, which means that delta H must also be doubled, which means 2 times 206. That's what it is. And then the next equation is reversed. All right, so which means that carbon monoxide and hydrogen gas are on the left hand side and the methane is on the right hand side, which means that we've actually reversed the reaction, which means we also have to reverse delta H, which means that now we have minus 206. So the forward reaction is endothermic, reverse reaction is exothermic. Now in the last equation, we have equation number C just doubled, okay, which means that we can take this final answer that we had from the previous one and double that. All right, so then our answer is 2 times minus 206. All right, which means that this is minus 412 or 412 kilojoules. So which one is the most exothermic reaction? The answer is the last one. All right, so after manipulating all of these equations, then you can figure out what the answer is. And the manipulation occurred only because delta H is a state function. So a little bit more, one more example, okay, and this is the first equation that we did before for sulfur. So in this combustion equation, the question is, write the thermochemical equation for the dissociation of 1 mole of sulfur dioxide. So 1 mole of sulfur dioxide. Remember, sulfur dioxide is in the product. So without showing you the answer, let's just do this in our heads for now. So if we're trying to figure out the dissociation of 1 mole of sulfur dioxide, it means that their equation is going to be reversed, which means the sulfur dioxide is actually the reactant, all right? Which means that if this is reversed, then this has to be also reversed, which means right now it's exothermic, it's going to be endothermic. And then the other thing is that it has to be for 1 mole of sulfur, which means that this is 8 moles of sulfur. So it means that we have to divide the delta H by 8, which means we have to divide the entire equation also by 8. So inverse the equation, and then first and then second part is divided by 8. So here's our equation, you inverse it, divide everything by 8. And so then this is going to be your final answer. Now, one of the things that I would like to tell you, and so you don't get panicky for this, until now, we've been using our equations. When we write our equations, we always use whole numbers, okay, which means 1, 2, 3, 4. We hardly ever use fractions and, never decimal points either. But when you're working with thermochemical equations, you can actually use fractions, okay, because if you're dividing by 8, then yes, you got to use this, okay. There is no other way to do this other than using fractions. So in thermochemical equations, you are allowed to use fractions. Okay, so now applying stoichiometry to delta H. So far what we were doing is inversing the equation and multiplying it by 2 and so on. But when you apply stoichiometry, it means that you're actually working from grams to moles. Okay, and then from there on we'll go on. Now we've done one such example before with the sulfur, but now again we're going to do some more. So same equation that we did before, all right, with the sulfur. So if you burn 15 grams of sulfur in air, how much heat is evolved? Now remember, we don't usually say if you burn 8 moles of sulfur, then how much energy is released, because when you say 8 moles is fine as far as, writing and calculating is concerned, but in our world, it's different because we actually measure in grams and not in moles. Okay, so we can't relate to that. It's much better to work in grams. So that's where stoichiometry comes in. All right, so the question is that you're burning 15 grams of the sulfur in air as a combustion reaction. So how much heat is going to be evolved? Okay, in this case. So You start your answer by calculating first the molar mass of sulfur. Why? Because you're given the grams. So when you're given grams, you're going to have to convert it to moles. So you need to know the molar mass of sulfur. Once you have the molar mass of sulfur, then you can calculate for the heat involved. And the heat involved can be Q or delta H, it doesn't matter. So you have 15 grams of sulfur. You convert that to moles first. So grams cancel out. And you have the moles of sulfur. And here you had 1 mole of sulfur 8 giving out 2.39. Okay, so that's what you then multiply it by. All right, and then you get your final answer, which is minus 1.40 times 10 to the power of 2 kilojoules. All right, so this is the heat given off by 15 grams of sulfur. Again, another example. The daily energy requirement for a 20-year-old man weighing 67 kilograms is 1.3 times 10 to the power of 4 kilojoules. And don't panic, this is in kilojoules, this is not in calories, okay? All right. Then, for a 20-year-old woman weighing 58 kilograms, the daily requirement is 8.8 times 10 to the power of 3 kilojoules. So if all of this energy were to be provided by the combustion of glucose, C6H12O6, how many grams of glucose would have to be consumed by the man and woman per day? So which means they're getting all their energy from glucose. And here is the combustion reaction that is given to us. Delta H is minus 2.82 times 10 to the power of 3 kilojoules. All right, so this is the equation we have to use. And of course, this is exothermic reaction because burning of glucose gives us energy. So here with, for a 20-year-old woman, okay, weighing 58 kilograms, this is what the setup would look like. Now remember, we'll start from what we know, which is 8.8 is what is 8.8 is the amount of energy that they have to actually consume. All right. Now that amount of energy, okay, is coming from 1 mole of glucose, which provides 2.82 times 10 to the power of 3 kilojoules, okay, of energy. Now convert that mole of glucose to grams of glucose by finding the molecular weight of glucose. And so the molecular weight of glucose is, of course, 6 carbon plus 12 hydrogen plus 6 oxygen. All right, and so that's 180.2 grams of glucose. So which means that a woman, a 20-year-old woman who weighs 58 kilograms, will have to eat 560 grams of glucose for her to survive every day. Okay, so the setup is going to be exactly the same for a 20-year-old man. You start with 1.3 times 10 to the power of 4 kilojoules. And if that is the amount of energy that is required, then you figure out how much is given off by 1 mole of glucose and then multiplied by the grams of glucose. So obviously, because the 20-year-old man is heavier in weight, 67 kilograms, he needs a lot more glucose, okay, to survive. So that is how you would set up for stoichiometry. All right, and again, remember, in stoichiometry it's important to convert grams to moles and moles to grams and all of that stuff, depending on what you are calculating for. So the key concept from this little portion of thermochemistry, we're not quite done. This is just the first portion of thermochemistry, is that you should know about the energy, different types of energy, and the units of energy. The units are calories and joules. You should be able to do the conversion. I didn't do any conversions here because you already know how to do those. So I expect you to do them in your homework and such. Then you should also know about the heat of reaction. By the heat of reaction, I mean exothermic, endothermic, and so on. Enthalpy, which is delta H. And then finally, you should be able to manipulate the stoichiometry and heat of reaction as in manipulations of delta H.